This is ACT Additional Math Concept Logic. Logic is what we are discussing here. You are going to need your own piece of lined paper for this. You may also want to have a ruler available if you have trouble drawing long straight lines, and you might also want to have a couple of highlighters. One highlighter may suffice, but two different highlighter colors might be better. So again, this is logic. I'm going to write in parentheses up here at the top of the page, conditionals. And what a conditional statement is, I'll go ahead and write down conditional statement. And on the next line here, I'm going to write if ... then ... That's all a conditional statement is. It's an if-then statement. And the if part, the first part, is known as the hypothesis. And the then part, the second part, is known as the conclusion. Those terms probably will not appear on the test, but you are going to hear me use them, which means you should be familiar with them. Again, the hypothesis corresponds to the if part of the conditional statement. The conclusion corresponds to the then part of the conditional statement. So what we're going to do here is we are going to sort of split this page up into some rows and columns. So let's go down, I don't know, let's go 3 lines down, and we're going to draw a long horizontal line. That was fairly straight, so that's good. And then we're going to draw 2 vertical lines splitting this page up into 3 columns. We're probably going to have to extend those vertical lines a little bit, maybe half a page length, 3/4 of a page length. We can extend them later if we need to. And what we are going to write here in this first column, we're going to label this first column conditional statement. Second column, we are going to label Venn diagram. Hopefully you are familiar with Venn diagrams. And then over here on the right, we are going to write down real life example. Real life example. I'm going to start with, of course, the original statement over here in the margin. Let's write down original statement. We're going to define this original statement as always true. We're going to give that original statement a truth value of always true. And the original statement will be very simple. It will be if capital A. We do use capitals in logic statements generally. If A, then B. Venn diagram. Now what we're going to try to do is we're going to use a Venn diagram to visualize what if A then B actually means. And what it means is that we would have this big circle B, and completely contained within that big circle B, we would have a little circle A. And indeed, you can see that if we satisfy the hypothesis by choosing an A member, in other words, an individual who is part of the A set, so this person or thing, or this person or thing, any of these points here, all of those points will satisfy the if A, the hypothesis, and we can see that every single one of those A's is also a B. So it is true that if you are an A, if you are contained within that A set, then you must also be contained within the B set, because the A set is completely contained within the B set. So if you satisfy the hypothesis here, the A part, then you will also necessarily satisfy the B part. So that Venn diagram represents what is going on in this conditional if A then B statement. Now the real life example, this probably will make things a lot easier to see in case anybody is struggling thus far. If you live in LA, then you live in CA. LA being Los Angeles, CA being California. It is true that if you live in Los Angeles, then you live in California. So what we've done is we've replaced A with you live in LA, and we've replaced B with you live in California. And if you look at the Venn diagram, you can almost imagine that the Venn diagram is sort of a map, and A is the city or county of Los Angeles, and that city or county is completely contained within the state of California. So it is true that if you live in Los Angeles, you live in California. That statement is always true. Now here's what tends to happen when students are given a conditional. We're going to draw a horizontal line here to make another row. Students will look at a conditional like if A then B, and they'll immediately start thinking of other statements that seem to be related or equivalent to this original conditional statement. One of the very common ones is if not A, then not B. So you notice what we've done there is we've just negated both the hypothesis and the conclusion. We've inserted these negations, these nots, in front of the A and the B. And in fact, we will call that the negation. Now, there is a technical term for negation. You probably are not going to need to know that technical term. Just in case, however, we will write the technical term there. It is called the inverse. The negation is called the inverse of the original conditional. So again, all we have done is we have inserted nots before the A and before the B. Now, in terms of the Venn diagram, what we're going to do is we're going to bring the same Venn diagram down. We're going to use the Venn diagram that corresponds to the statement that we defined as always true. And what we're going to do, so again, we're just bringing that same Venn diagram down here. And what we're going to do is we're going to see if this negated statement, this inverse statement, has the same truth value as the original statement. And indeed, if we pick this individual out here, we satisfy the hypothesis. That person is not an A, and that person is not a B, so we also satisfy the conclusion. So for that individual, we do get somebody who satisfies both the hypothesis and the conclusion. However, if we choose, for instance, this person right here, and I'm going to highlight that person because that person's the important one here. Notice that that person satisfies the hypothesis. Okay, that person is not an A. That person is outside of the A circle, but that person contradicts the conclusion. That person actually is a B. We wanted the conclusion to be then not B. So what does that mean? That means that when we simply insert nots before the A and before the B to create the negation, we don't get a statement that is necessarily true. In other words, we don't get a statement that is always true, which means we don't get a statement that is logically equivalent to the original statement. There are counterexamples, and in fact, that's what this is right here. We're going to write down counterexample. A counterexample is any individual or any item, any element of a group or a set that satisfies the hypothesis but does not satisfy the conclusion. So this person, this individual right here, is a counterexample to the statement, if not A, then not B, because that person is not an A but is a B. So we're going to write over here in the margin, we're going to write not necessarily true / not logically, let's do this, logically equivalent to the original statement. So again, the negation is a statement that a lot of students assume is true. They think it's very logical to simply insert some nots in the original statement. But we can see that because there are counterexamples to this if not A then not B statement, that statement is not necessarily true, which means that statement is not equivalent to the original conditional, which we defined as always true. Now, a third statement that we need to discuss here is this one, if B then A. Notice that all we have done there is we have swapped the hypothesis and the conclusion. The B went from the conclusion to the hypothesis, the A went from the hypothesis to the conclusion. We are going to call this the reversal. The technical name is the converse. And let's take a look again. We're going to use the same Venn diagram that we started with, because that original Venn diagram was the one that we defined as always true. And what we do here, if B then A, well, let's look at this person. That person right there again satisfies the hypothesis and satisfies the conclusion. That person is a B. That person is contained in the B set, so the hypothesis is satisfied, and that person is also an A. But that little guy right there that we used before, he's going to be a problem again, or she, either one. That data point right there, if one does exist, that person will satisfy the hypothesis. That person is a B, so the hypothesis is satisfied. But that person contradicts the conclusion, then A. That person is not an A. That person is outside of the A set. So once again, that point right there serves as a counterexample to our reversal here. And remember what we set up here. If a counterexample exists, then the statement is not necessarily true. It is not necessarily true that, so we're going to write not necessarily true, not log equivalent to the original statement. We said that if we can find someone or something that satisfies the hypothesis but goes against or contradicts the conclusion, then the statement is not always true if there are counterexamples. So the reversal is not logically equivalent to our original statement. Now, by the way, in terms of your real life examples over here, you actually may want to pause the video and try to form the negation and the reversal for our original real life statement. I'm going to go ahead and form them right now, and doing so will make hopefully all of this stuff come together if you're a little bit shaky. So here is the negation. If you do not live in LA, then you do not live in California. Well, that's clearly not true. There are many cities in which you can live in California. You don't just have to live in Los Angeles. You could live in San Francisco or San Diego or Fresno or a bunch of different cities. So it is not necessarily true that if you don't live in LA, you don't live in California. It could be true, but it doesn't have to be true. And this person right here, who does not live in LA but does live in California, again, is a counterexample to this statement. That person does not live in LA but does live in California. And then down here with the reversal, if you live in California, then you live in LA. Well, again, that person right there who lives in, I don't know, San Francisco or San Diego shows that this statement is not necessarily true, because that person does live in California but does not live in Los Angeles, which means that this person satisfies the hypothesis but contradicts the conclusion, does not satisfy the conclusion. So hopefully that all makes sense. And now we have to talk about the most important derivation of the original statement, and that is going to be this. If not B, then not A. And if you just pause there for a moment and take a look at what we did two things. We actually combined the negation and the reversal. Notice that once again our hypothesis and conclusion have switched spots. We had A, B first, now we have B, A. And we inserted the nots. So we both negated and reversed. So let's write down negation and reversal. And the technical name for this one is contrapositive. The contrapositive. Now let's take a look at our Venn diagram, and then we'll look at that real life example. So we're using that same Venn diagram with the A set completely contained within the B set as was defined by our original statement. And remember what we did in both of these cases is we first tried to satisfy the hypothesis. Hypothesis satisfied, 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 satisfied. So if we try to satisfy the hypothesis here, the if not B, well, remember that means we need to take an individual or item from outside the B set. So is there a way to take an item from outside the B set, in other words, again, satisfy the hypothesis, is there a way to take someone from outside the B set and contradict this conclusion? The answer is absolutely not. If we pick an individual from outside of the B set in order to satisfy that hypothesis, we also always satisfy the conclusion. Everybody from outside that B set is also not captured within the A set. Every member, I should say non-member of B is also a non-member of A. There is no way that you can be outside of the B set but be inside the A set, because the A set is completely contained within the B set. The contrapositive over here for the real life example, you may want to pause the video for a moment and see if you can derive it. Shouldn't be too difficult. The contrapositive here would be if you do not live in California, then you do not live in Los Angeles. And that is absolutely true. There is no way that you can live outside of California and still live in LA, except maybe in your heart or mind. But that's figurative stuff, and that's not what we're talking about on the math section of this test. So if you don't live in California, then you don't live in LA. That's absolutely true. All of these people do not live in California. There is no way those people can live within the city or county of LA. So what we have just found is the contrapositive. If we define that original if-then statement up here as always true, the contrapositive is also always true, and the more important thing about the contrapositive is that it is logically equivalent to the original statement. So if our original statement is if A then B, then the contrapositive, and if not B then not A, is always true. Let's take a look at an example of how this might be tested on the test. So down at the bottom of the page, let's go ahead and write down EX. In fact, I will give you one from a previous test. So they gave in the question the statement, if a cat is tricolor, then it is female. What I would, and then what the question would ask is which of the following statements is logically equivalent to that statement. So what you might want to do is pause the video and see if you can form the contrapositive of this statement. I am going to do that right now. So here is the contrapositive. If not female, then not tricolor. So if a cat is not female, then that cat is not tricolor. So notice what I have done. I have swapped the hypothesis and the conclusion. Tricolor went there to the end, female went there to the beginning in the hypothesis, tricolor in the conclusion, and I have negated both halves of the statement. So if not female, then not tricolor is the contrapositive of that original statement, and the contrapositive is the only statement that is logically equivalent to the original statement. So something like if the cat is not female, then the cat is not tricolor would be the answer to a question that asked about logical equivalency. Now, just to hammer these points home, especially the point about the contrapositive, how to form it, let's do a couple more examples. Also, this will show that the way that we form the contrapositive is consistent from statement to statement, from conditional to conditional. So if we have a statement that is something like if not R, then S, and we want to form the contrapositive, we can see that our hypothesis is not R and our conclusion is S. So what we will do is we will swap those. So we will do if, I'm going to leave a little bit of space here, if S, then not R. So again, I've just swapped the hypothesis and the conclusion. That's the reversal. And now remember what I need to do is I need to negate. So I need to insert a not before that S. And then negating this not before the R, in other words, doing not R. Well, remember, not R means R. In other words, negating a not, notting a not, just gets rid of both of the nots. It's almost like it's a double negative, and a double negative makes a positive. So our statement would become, if not S, then R. That statement would be the contrapositive of this original statement. Let's do one more. Let's do if not X, then not Y. Go ahead and form the contrapositive of that statement on your own. Maybe pause the video. So the contrapositive of that statement, again, our hypothesis is there, our conclusion is there. They reverse and we negate. Negating the two nots is just going to end up with not nots again, which means just positive. So we will have if Y, then X. So if Y then X is the contrapositive and logically equivalent statement to if not X, then not Y. By the way, you also could go in the opposite direction. That original statement, let's say that the contrapositive actually happened to be the original statement, then this statement up here would be the contrapositive of this original statement. Same thing over here. If not S, then R. The contrapositive of that statement would become if not R, then S. Finally, last thing, just want to re-emphasize that whole idea of a counterexample. Remember that a counterexample, I'm going to try to squeeze this in here, counterexample is any person or item or individual that will satisfy the hypothesis but contradict the conclusion. So in the case of our cat example, if I were able to show you a tricolor male, a tricolor male would be a counterexample to this statement because that statement is tricolor. In other words, we satisfy the hypothesis, but it is not female. It's male. So it is not female, which means that a tricolor male satisfies the hypothesis but contradicts the conclusion, which means a tricolor male would be a counterexample to this statement. That is it for logic. Again, the big takeaway here is the contrapositive. You will need to know how to form the contrapositive. You do need to know that on a lot of the logic questions that have shown up on this test, the questions were as simple as homing in on the contrapositive among the answer choices.